All right, everybody, we're going to work on the first section of chapter 8 today, which is going to be exponential growth and decay. The two learning targets, you're going to be able to graph these exponential growth and decay functions. The bright thing is it's going to be exactly the way we've been graphing for the most part throughout this semester. And then also we're going to be able to use exponential functions to solve real life situations. So I have 3 different word problems, all of which will be represented on the test when we get to there. We're a long ways from there now, but then only one of these 3, though, is going to be on today's learning target. Okay, let's talk about just some general ideas or concepts behind an exponential function. Any exponential function is going to be in the form y equals a times b to the x power, where a cannot be 0. And if b is greater than 1, it's going to be considered a growth function. And what is going to be true about that function is that means from left to right, the graph is going to start here and it's going to slowly increase, and then it's going to kind of hit a threshold and just increase quite quickly. What's the domain? Remember, domain is what numbers can you plug into this function and get out a valid y value, and that's going to be all real numbers. So that's going to be true for all of these exponential functions, is that it's going to have a domain of all real numbers. Now the range can vary, but for the most part, similar to our rational expressions where we had a vertical and horizontal asymptote, as I go this direction, the graph will decrease by cutting in half or thirds or whatever it may be repetitively over and over again. And it creates a horizontal asymptote at y equals 0. Meaning the graph is never going to touch or cross that value. So that means my graph is at 0, but it never touches or crosses it and is strictly above it. So the range of this function is going to be y is greater than 0. Okay, it's not greater than or equal to, because it's never going to hit or cross that red line, but it is going to infinitely approach it, creating an asymptote, which is exactly what that is. Okay, an exponential decay function, that is an equation in the same exact form. A also can't be 0, but in this situation, B is less than 1 and also greater than 0. So if your B value is in between 1 and 0, it's going to be a decay function. The thing that's nice about growth and decay functions is they mostly share the same characteristics. The only difference is growth increases from left to right, decay decreases from left to right. The domain is also going to be the same value, and the range is also going to be the same. So it makes some aspects of these problems pretty easy. Remember, a times b to the x power is b is in between 0 and 1. It is growth, or it's decay. If it's greater than 1, it's growth. Okay, here's the first problem. We have y is equal to 2 to the x power. So in this particular problem, we know that it is an exponential function because it's in this form. And it's beneficial for us because we want to identify this function as growth or as decay. So since it is, so we're going to want to find the a and the b value. So here my a value is 1 because there's no number here. So it's 1 times 2 to the x power. So b is the value that has that exponent. So b in this situation is 2. Since the b value is greater than 1, this is a growth function. Okay, now that I have that done, all that's left is to graph it. Okay, so I'm going to go ahead and do the same thing that we've been doing basically all semester. Take out our calculator, hit y equals, clear out anything that's in there. Okay, and then just go 2 to the x power. Remember, the exponent button is right here, and your variable button is right there. Okay, you can look at the table of information by hitting second graph. Okay, and you want to find the ones that just kind of best fit the graph. 32 is off the graph, so 16. Here's the first one, 3, 8. So 3, 8 on the graph. 2, 4. 1, 2. 0, 1. And -1, 1/2. I suppose I can do a half. That's going to be pretty easy. And oops, didn't mean to do that. And, 0.25 is a little harder to graph, so I'm content with this list here. About 5 numbers is typically what you're going to get. Okay, so let's go ahead and graph those. Negative 1.5, 0, 1, 1, 2, 2, 4, 3, 8. So then I'm going to take this and I am going to connect them all in a smooth curve. Try to keep it above the x-axis because we know we have an asymptote there. If it touches, it's not the end of the world, but if you do just diagonal it way down here, I am going to count that as wrong. Okay, now it's important to know that we know that this is an exponential function strictly by looking at the data set. As the x's increase by 1, the y's are doubling every single time. Since they're doubling every single time, that's literally what an exponential function does. It's repetitive multiplication over and over and over, or division. Okay, so I'm going to leave example A for you to do on your own as part of your practice. So let's go ahead and move on to page 3. Okay, so here is the first of 3 types of word problems that you're going to have. Okay, so some real quantities increase or decrease by a fixed percent each year or some other time period. The amount y of such a quantity after t years can be modeled through one of these 2 things. It's going to be either exponential growth and exponential decay, where 1 plus r is your b value. So if r is 5%, 1 plus 5%, that's going to be greater than 1, so it's growth. Here, this is a decay function. 1 minus r is my b value. So again, if my R value is 5% decrease, 1 minus 5% is going to be less than 1. So therefore, that B value is less than 1, and it's a decay function. So let's go ahead and look at this. So the value of a car in thousands of dollars can be approximated by the model y equals 0.25 or 0. Oh my Lord. Okay, y equals 25 times 0.85 to the t power, where t is the number of years since the car was new. So tell whether the graph represents the model represents exponential growth or exponential decay. I can think of 3 reasons. When it comes to you only need to give me one of these 3. So whatever best fits your understanding. The first reason is the B value, which is 0.85, is less than 1. Okay, so since it's less than 1, I know that this is going to be an exponential decay function because the B value, 0.85, is less than 1. If it's less than 1, we learned in the previous page, that's a decay function. The second thing, it does give me the graph here. We know that it is, the graph is decreasing. Since the graph is decreasing, we know that that is going to be an exponential decay function. And then the last reason I know that this is a decay function is the third reason, and that is in this situation, we're talking about the price of a car. And unless it's some special collector kind of car, cars depreciate value. They lose value the minute you drive them off the lot. So cars lose value. Okay, so if you want to give me a contextual reason, a reason based on the graph, or a reason based off the equation, any of those 3 are going to be just fine with me. So now that we know it's decay, we want to find the annual percent increase or decrease of the car. So what does this mean? Well, it probably helps to know what A, R, and T represent. Well, we know A in this situation is going to be initial value. Probably should have started with this. R is going to be the percent increase or decrease. And T is time. So I want to find that R value. So I know the exponential decay model, the B value is 1 minus R. So I know 1 minus R is equal to 0.85, the B value. So all I have to do is solve for R in this situation. So this number here is going to be equal to this. They're both in the sets of parentheses. They're both being raised to a power. And so all I have to do is solve. So minus 1, the opposite of R is equal to negative 0.15. and divide by -1, R is equal to 0.15, which is a 15% decay. So what does this mean? This means that this car loses its value by 15% every single year. So in this situation, Y is the value of the car in thousands of dollars. So it has an initial value of $25,000 and it's losing 15% every time. So if it's losing 15%, that means it's retaining 85% of its value year after year after year, but it's still losing that 15%, so it's decreasing. Okay, estimate the value of the car when the value of the car will be 8,000. So the question is Y equals 8,000. So we know 8 is equal to 25 times 0.85 to the t power. Now, we do not know how to solve for these t variables yet. That's actually the point of this whole chapter later on. But right now, we do have the problem-solving skills to do this. If I were to be given the graph of it, like I have here, I could just go ahead and find when is the y value roughly 8. And as we can see, it's going to be approximately 7 at x value 7. Its y value is at approximately 8. You can see that represented here. But that seems a little more difficult than what it is. Rather, a student in my other class said, well, we could just graph it, but instead of looking at the graph, we could look at the table of inputs and outputs. So that's exactly what we're going to do. Oh, that's too bright, huh? So I'm going to go ahead and take this equation, y equals 25 times 0.85 to the x power. Now, I can't type the t in there. The calculator will really only take the x variable, but it will function the same. X will just be years for us. So here I hit second graph. Go ahead and look at my table of inputs and output. After 1 year, the car's worth $25,000, or after 0 years, it's a $25,000 car. After 3 years, it's about $15.3 thousand. So now what I have to do is just try to find when it's approximately 8,000, which this is about as close as I get. Y is 8.01 and X is 7. So how long after we buy this car is it going to be worth $8,000? After about 8 years. So after about 8 years, the car's worth about, or not 8 years, 7 years, sorry. After about 7 years, we know the car's worth about $8,000. So that would be my suggested method to you. You could 100% graph this thing and try to find the Y value, but I think it's just easier to look at the table and just give me a rough estimate of that. Okay, similar to the previous problem, the letter problem B is going to be for your practice today. So let's go ahead and save that for later, and let's just keep pressing through here to part 3. This one, we have to write the exponential equation. In 2000, the world population was about 6.09 billion. During the next 13 years, the world's population is going to increase by 1.18% each year. Part A, write an exponential model giving the population Y in billions, t years after 2000. So it's important to note Y is in billions and t is in years after 2000. So that means if my Y value is 10, that's 10 billion people, not just 10. If Y is 3.8, that's 3.8 billion people, not just 3.8 people. T is years after 2000. So if T is 7, I'm in the year 2007. If T is 15, I'm in the year 2015. Currently, this video is being recorded in the year 2023. So to represent the year 2023, that would be a T value of 23. Okay, so we're going to write an exponential model of the population. The first thing we need to know is growth and decay. So in this situation, you have to understand the context of the problem and understanding that the population is increasing. Since it's increasing, this is going to be an exponential growth model. Okay, and I have this memorized, but you can get the growth model based off the previous page. So A, it's going to be initial amount. So for us, that is going to be 6.09. R is the percent increase or decrease, which for us, 1.18%. And this is an important concept. It must be as a decimal. So I need to convert this into a decimal. And it's really easy. You just divide by 100. So 1.18 divided by 100 is 0.0118. So that's the number I need to use. And T is time. We don't know. We don't have the time quite yet. That will be for part B. So really easy. Y equals 6.09 times 1 plus 0.0118 to the T power. And then I just have to add these two numbers together, 1.0118 to the T power. So my model is Y equals 6.09 times 1.0118 to the T power. Okay, part B. Part B says, estimate the population in 2005. So what T value represents 2005? I hinted at it earlier. 2005 is 5 years after 2000. So this is T is equal to 5. So all I have to do is take this equation, and instead of T, I'm going to write 5. Okay, and then all I do is type that into my calculator exactly the way it's written on my paper. We should know how to do exponents by now. Okay, and then you just hit enter, and it's about 6.46 billion. Okay, part C. Estimate the year when the population was 7 billion. So we know in this situation, Y is going to be equal to 7. So what I'm going to do is I'm going to type this into the graphing portion of the calculator, and I'm going to scroll through the table like I did on the previous problem until I get an approximated Y value of 7. So I'm going to take my calculator. I'm going to clear out the graphing part of it. So I hit Y equals and cleared it out. 6.09 times 1.0118 to the X power. Again, you don't have T, so. Okay, so now what I want to do is I'm going to hit second and graph to look at the table. And I got to find a Y value that's approximately 7. So I'm at 6.689. Keep going. Get closer. Okay, probably right around 12. So approximately 12 years, I'm going to be at a roughly 7 billion. So it's like T equals 12 years, which is what year? 2012. And that will be roughly the time where the population is going to be 7 billion. Okay, again, letter C is going to be practice for you, so I'll let you guys do that at the end. Otherwise, let's move on to the last compound interest problem. Okay, so often money is grown in an account. It's compounded more than one time in a year. It can be compounded about as many times as you would like. It just depends on the account that you have. So considered under an initial principal deposited in an account that pays interest at an annual rate R, expressed as a decimal, compounded n times a year, the amount A in the account after T years is given by this formula. So let's go over those. Capital A, money in account. P, principal, which is the starting amount of money in the account. Okay, so whatever was deposited initially, it's the initial amount. Okay, R is the percent, has decimal. N is number of times compounded in a year. and T years. So often N is the most complicated of those. So let's talk about this. If something is compounded monthly, that means it's going to be compounded 12 times in a year. If something is compounded every 4 months, it means it's compounded after the first 4 months, the second 4 months, and the third 4 months, compounded 3 times, compound N value would be 3. Compounded every day, it'd be 365. If it was compounded every 6 months, it would be 2. So you just have to ask yourself how many times compounded in a year. Okay, let's start number 4. You deposit $9,000 in an account that pays 1.46% annual interest, which is way higher than a savings account you'd ever get. Find the balance after 3 years when interest is compounded quarterly. Okay, so all I have to do is find all of these values. A, we don't know that. That's what we're finding. P, principal. The initial amount deposited, that is 9,000. R is the percent as a decimal. So what's my percent? I'm getting 1.46%, which is, divide that by 100, 1.0146. Okay, T, 3 is 3 years, and N, compounded quarterly. So if it's compounded quarterly, that means it's splitting it up into 4 parts, like a quarter is 4 parts of $1, and value is 4. So what I'm going to do is I'm going to write this equation with these values in it, and I will show you how to simplify it. So A is equal to 9,000 times 1 plus 0.0146 divided by 4 to the 4 times 3 power. So all I'm doing is replacing N with 4, T with 3, 0.146 with R, and P with 9,000. Okay, so I'm going to show you how to simplify this. It's quite simple. First off, 4 times 3 is going to be 12. So we're going to just assume that we know how to do that. So here, the first part is 9,000 times. We got to figure out this inside number. This is how you do it. Take your calculator out, clear out what you have. 0.0146 and then divide it by 4. Hit enter. Once you get that, plus 1. Okay, generally speaking, let's just round to 4 decimal points on the inside of this number here. So we'll go 1.0037 to the 4 times 3 power 12. Okay, so once you have that, really all we have to do is type this whole thing in the calculator and go. So 9,000 times 1.0037 to the 12th power. Hit enter, and that's how much money is in the account. So after 3 years, we're going to have $9,407.83. Okay, so like I said at the beginning of the lesson, you're going to have all 3 types of word problems when it comes to the assessment, but for the learning target, it's just going to be one of these 3. So go ahead and take some time practicing all 4 lettered problems, A through D. When you're done with that, move on to your learning target. Otherwise, I'll see you folks next time.